Okay, hi everyone. Yeah, thanks for the organizers for giving me the opportunity to present this talk. So I'm going to be talking about a recent archive posting that I made about 2.5 weeks ago, in which I talked about an adaptation of 2019 arguments for renormalizing crossing probabilities. And this argument was originally due to Dumino, Copan, and Tassion, and they proposed an argument that could be used to obtain Russo-Seymour-Welsh results for models in statistical mechanics that are not self-dual, and they proposed that this similar type of arguments could be obtained for other models that are not self-dual. And so for our preliminaries, classical Russo-Seymour-Welsh or RSW arguments have been applied to Bernoulli percolation. And we know that this is an example of a self-dual model because from Kessen's seminal 1980 paper, the critical point of Bernoulli percolation is a half. And at this critical parameter, the model and its self-dual model are each Bernoulli percolation with parameter half. So it's of interest to determine whether these Russo-Seymour-Welsh arguments can be obtained for other models in statistical mechanics that are not self-dual. And so for a presentation overview, I'm going to describe how the argument applies in the case of the random cluster model from 2019, which can then be applied to the dilute Potts model that was introduced by a Dutch physicist in his 1991 paper. And the overarching goal of our analysis will be to classify four regimes of behavior of the dilute Potts model from the light of the estimates for crossing probabilities that are given for the random cluster model. And our prize is a Russo-Seymour-Welsh or RSW result is characterized by an inequality of the following form. From the first item that I've denoted, if we have phi as the random cluster measure, the support of this measure is given in the subscript of the probability measure. And in the second item that I've indicated, we look at a horizontal crossing event across a rectangle of aspect ratio rho n, where rho is greater than 0, and independently of the boundary conditions which are indicated by the third item, which is given in the superscript of the probability measure, independently of these conditions, the horizontal crossing probability is bounded below by C of rho and above by 1 minus C of rho. And historically, such results have been of interest because the crossing probability is non-trivial and it degenerates to neither 0 nor 1. And briefly, I'll provide some detail on the random cluster model and then transition to the loop-O(n) model. So the random cluster model is a measure on random subgraphs of the square lattice. It's given by the probability measure phi with boundary condition C, whose support is given by G. And the random cluster configuration of omega is given by the reciprocal of the partition function times the ratio P over 1 minus P, which respectively indicate the probability of selecting either an open or a closed edge from the random cluster configuration, which is collectively raised to the number of open edges times Q to the number of clusters. And the main technique that's used to obtain Russo-Seymour-Welsh results for this model that is not self-dual is that we introduce strip densities for wired and free boundary conditions. Namely, the first quantity that we define is Pn, which is the limit supremum as alpha tends to infinity of the random cluster measure taken under free boundary conditions of a horizontal crossing probability across aspect ratio alpha for positive alpha that's raised to the reciprocal of alpha, in addition to a similar quantity for the vertical crossing probability that's given by Q of n, which is the limit supremum of the random cluster measure under wired boundary conditions, in which instead we take the complement of a vertical crossing event that's raised to the reciprocal of alpha. And the random cluster measure satisfies the following properties. If we have A and B as two increasing events, it satisfies the FKG inequality, which states that under the random cluster measure, the intersection of two increasing events occurring is bounded below by the product of each one of the probabilities. It also satisfies the spatial Markov property, which states that if we have two finite volumes G and H, with G embedded within H, we know that random cluster distribution on the larger finite volume H by taking all of the vertices that are from the boundary conditions in C from G, in addition to appending additional vertices that are given in C prime from additional vertices that are given on the boundary of H. And finally, the comparison between boundary conditions states that if we have one boundary condition C, which dominates C, then the inequality holds in which the dominant boundary conditions forms an upper bound. In a special case of the comparison between boundary conditions that they implement is that they have a special factor which is of the form Q to the maximum minus minimum number of clusters. And the strip and renormalization inequalities for the random cluster model take the following form. Roughly speaking, our objective is to renormalize horizontal and vertical crossing probabilities on smaller scales with crossings across larger scales. First, the strip inequality comes in two variants. In one version of the inequality, we have a horizontal crossing probability across a scale 3n, which is bounded below by vertical crossing probability across scale n that's raised to the reciprocal of some parameter lambda, where lambda is greater than or equal to 2, in addition to the second variant, which states that the vertical crossing probability across scale 3n constitutes an upper bound for the horizontal crossing probability across scale 3n raised to the reciprocal of lambda. And the renormalization inequality takes the following form for horizontal and crossing probabilities alike, in which we have that a horizontal crossing probability across scale 3n is upper bounded by a horizontal crossing probability across scale n, again raised to some quantity that's inversely proportional to lambda, in addition to another version for the vertical crossing probability event. And now we can transition to the loop ON model, which is another model in statistical mechanics that's not self-dual. First of all, we have a probability measure on loops, which is given by a Gibbs measure, which we indicate as boldface P. It has boundary condition C, and the support of the measure is given by the finite volume given in the subscript of the probability measure. And the probability of sampling this configuration sigma is given by x to the number of edges and to the number of loops, normalized by the partition function. And the boundary conditions C, as I've indicated here, they can either be all open, all wired, or a mixture of wired and open boundary conditions. And we can pass to the high temperature phase of this model by appending an exponential factor that's a function of two external fields, H and H prime. We denote this high temperature spin measure as mu tau, a g of xn. Sigma prime is the spin configuration from the dilute Potts model that we would like to sample, in which for the first external field, H, we have a multiplicative factor R of sigma prime, which is given by the summation over all spins over a finite volume, in addition to another corresponding multiplicative factor for the second external field, H prime, which is R prime is sigma prime, which is given by the number of monochromatically colored triangles.
Is it K and the L?
Sorry?
Is N to the L sigma and N to the K sigma prime? Are they the same?
Oh yeah, sorry, yeah, that's they're the same. That's n to the number of loops, that's n to the number of connected components.
Oh, I see, okay.
Yeah, I'm sorry.
Okay, yeah.
And there's a correspondence between this high temperature spin measure and Nienhaus's dilute Potts model that he analyzed in his 1991 paper. From this paper 30 years ago, we have the following correspondence. We have this spin measure that's given at the top of the slide. And then we know that the correspondence is constituted of the following three items. First, we have all of the dual monochromatically colored triangles over the dual of the hexagonal lattice to the triangular lattice. We have the summation over all spins over a finite volume, in addition to the number of edges in loop that we sample in the configuration. In the Boltzmann way that he introduces in his paper admits the following decomposition. It decomposes as a nearest neighbor product and an exponential factor. And if we look at the exponential factor first, the constants K1, K2, and K3 are all positive. And the factors that we have in front of each or behind each of these constants respectively denote the summation over all spins, the occupancy in which the Ti-Tj factor can either be 0 or 1, in addition to the number of monochromatically triangles Ti-Tj, Tk. And for the nearest neighbor product, we incorporate spins from the Q-state Potts model with Sj and Sk terms. And what qualifies this Potts model as dilute is that if one takes the positive parameters K1 and K2 and K3 to be small, then the probability of obtaining a hexagon that's colored black is very small compared to the probability of obtaining a hexagon that's colored white. And the dilute Potts model satisfies its own version of the comparison between boundary conditions and the spatial Markov property. For the high temperature spin measure, I'll denote SCBC as the spin comparison between boundary conditions. If we have two pairs of boundary conditions, tau and tau prime dominates tau, then we know that we can have the following special form that's for the high temperature measure. If we have if we have one inner domain here whose 6 sides are labeled from the hexagon, we can obtain an outer domain by dilating one of the sides to obtain a slightly larger volume and our weak infinite volume limit. And the impact of a single monochromatically colored triangle is felt by the second external field H prime, in addition to a difference in the number of edges and a difference in the number of connected components. And for the spin spatial Markov property, we know that the distribution of the dilute Potts model under outer domain O, if we know the boundary conditions T on the inner domain I, is given by appending the boundary conditions tau prime to this high temperature measure. And finally, it also satisfies the FKG inequality, in which for A and B as two increasing events, the intersection of the probabilities can be bounded below by the product of each one of the individual probabilities. And the dilute Potts model satisfies the following quadrichotomy. We have 4 phases of interest for the model. We have the subcritical, supercritical, continuous critical, and discontinuous critical phases. In the subcritical phase, we know that even if we look at the high temperature spin measure under wired boundary conditions, which realistically would make the prospects of a horizontal crossing event occurring the most likely, this probability decays exponentially fast. Whereas in the supercritical phase, under free boundary conditions, the horizontal crossing probability is bounded below by 1 minus an exponential. In the continuous critical phase, we have the Russell-Seymour-Welsh property, which takes the following form, the same form that I indicated to you in the random cluster model. And the discontinuous critical phase is a mixture of the subcritical and supercritical phases. And we can define horizontal and vertical strip densities for the dilute Potts model by looking at free boundary conditions, in which we look at the horizontal crossing event occurring, or we look at the complement of a vertical crossing event occurring under wired boundary conditions. And the renormalization inequalities take the following form. We have similar ingredients for constructing auxiliary asymmetric domains, which are some technical arguments that have to be brought in because the model is not self-dual. And the exponent to which the crossing probability is raised is dependent on some integer in the parameter in which we dilate our finite volume to obtain an infinite weak volume limit. And after we execute arguments to take into account for intrinsic spatial dependencies of the dilute Potts model, we can prove the Russell-Seymour-Welsh results that are characterized in the continuous critical phase of the model. We recall that for the random cluster model, the Russell-Seymour-Welsh results for horizontal crossing probability take the following form. And for a sketch of our proof, for the first step, we configure 4 finite volumes as shown. We have the centermost blue hexagon that's given by region R1, in addition to a slightly larger hexagon that's given by the region R2. And then we flank to the left and right the centermost blue region with regions R3 and R4. And we can obtain the constants that are C and 1 minus C that are given in the Russell-Seymour-Welsh results by looking at the probability under the high temperature spin measure under mixed boundary conditions of a horizontal crossing event occurring across region R1. And we can bound this below as indicated. We can bound the event that's given in the upper bound for the second step with the event that's given in the lower bound for the third step that's dependent on the horizontal strip inequality, which is given by rho P alpha rho to the n. And similarly, if we consider a different conditional horizontal crossing event in which under the high temperature spin measure, we enforce the conditioning of the horizontal crossing event across R1, we can obtain a lower bound for the that's dependent upon the vertical crossing strip density, which is given by q to the gamma n over 3 across a slightly smaller scale. And together, we can obtain the Russell-Seymour-Welsh results by multiplying inequalities for horizontal and vertical strip densities together. And the constant that's given for one of the Russell-Seymour-Welsh constants is provided in the lower bound, which is precisely given by a product of horizontal and vertical strip densities. And for the fifth and final step, we can synthesize our results to obtain Russell-Seymour-Welsh results with constants C and 1 minus C, which is given from the classical results for a model that's not self-dual. And I would like to thank Philippe Sosue for providing me with comments on this presentation. And also in future work, I'm interested in looking at results for the 6-vertex model from crossings of the height function. And thank you for listening. Are there any questions?